In this video we will discuss the idea of an indefinite integral and what it means to perform indefinite integration. So what you'll notice is that you have your integral sign here, but you do not have bounds. Okay, so we don't have from a to b, we just have an integral sign. Of some function is equal to capital F, which means it's equal to the antiderivative of this function on the inside. So that's all we are doing when we do an indefinite integral. We are simply just taking antiderivatives. You can look through this table on your own, but basically it's just saying that no matter what the function is, when I'm doing an indefinite integral, I'm just going to find the antiderivative and make sure to put plus c when we do that. So we've got a couple of examples of indefinite integrals and then a couple of examples of definite integrals just to show you the difference between the two. The first step for each is essentially the same. Once I simplify the inside of the integral, it's to just take the antiderivative. So on number 1, the antiderivative of 10x to the 4th would be 2x to the 5th. The antiderivative of secant squared x is tangent x. And then I'm going to be sure to put plus c. And that is all that you do when you are finding a general indefinite integral. On number 2, we've got a little bit of work that we need to do before we integrate. We have cosine x divided by sine squared x. So I'm going to simplify this down. I'm essentially going to take this sine squared and I'm going to leave one of those underneath cosine. And I'm going to think about the other one as being just a 1 over sine x. So I want to think of this as 1 over sine x times cosine x over sine x. All of that dx. Which means 1 over sine x, that is cosecant x. And cosine x over sine x is cotangent x. And so then I can look at this as the integral of cosecant x cotangent x, which we have here, which says it is equal to the negative cosecant of x plus c. So when we evaluate, we just get the antiderivative of that, which is negative cosecant x, and then plus c. Okay, jumping down here, we're going to look at some definite integrals. So again, the first step is the same, regardless of if it is a definite integral or an indefinite integral. The first step is to take the antiderivative. So what I'm going to do here is I'm going to take the antiderivative of the inside function here, which would be 1/4 x to the 4th minus 3x squared. And then what I do is I evaluate that over the interval from 0 to 3, which means I'm going to evaluate this at 3. So 1/4 times 3 to the 4th minus 3 times 3 squared. And then I'm going to subtract what I get when I evaluate this at 0. So 1/4 of 0 to the 4th minus 3 times 0 squared. And if you evaluate that, this is all 0 because we're plugging in 0 into a polynomial. So we essentially just need to evaluate this part, which gives us negative 27/4. So obviously we have a few more steps there with a definite integral than an indefinite. Again, you don't have to put the plus c. I mentioned this in a previous video over the fundamental theorem of calculus, but I don't have to put plus c because those are just going to cancel each other out. But the main idea is we do, just like we do with an indefinite integral, we take the antiderivative and then we plug in our bounds and subtract. Number 4 is a little bit more complicated here. I need to simplify the inside here first. And so essentially I'm just going to take each term and divide by x squared. So that 2x squared is just going to become 2 when I divide it by the x squared. When I take this middle term and divide by x squared, essentially what's going to happen is the x squareds would cancel and I'd be left with the square root of x. So that's going to be, I'm going to rewrite that as x to the 1/2 power so that I can take the antiderivative of that. And then we have minus 1 divided by x squared. Well, 1 divided by x squared would be x to the negative second. So that's what I would get if I were to divide each of those by x squared. I did forget on the initial problem here to put a dx. There should be a dx there. Now I can take the antiderivative and evaluate. So that's going to be 2x plus, this would be x to the 3/2, which means our coefficient would be 2/3. And then minus, this would be x to the -1st, which means I'm going to divide by -1, which means this is going to become plus x to the -1st. And we're going to evaluate that from 1 to 9. So if I evaluate that at 9, 2 times 9 plus 2/3 of 9 to the 3/2 power plus 9 to the -1st. And then we subtract what we get when we evaluate this at 1. 2 times 1 plus 2/3 of 1 to the 3/2 power plus 1 to the -1st. Work through all that, and you could pause the video if you want to and work through and see if you get the same answers here. But if we work through all that math, you end up with an answer of 32 4/9 is what I ended up with. 32 4/9, or an equivalent decimal or equivalent improper fraction. So my main point of putting these last two on here is just to explain to you the difference between an indefinite and a definite integral. Before this video, you should have hopefully seen how to evaluate a definite integral, but it's the same idea. Indefinite integral, we are just taking the antiderivative, whereas definite, we can plug in those bounds and figure out that exact area under that curve.